Hi again. I'm back from skiing and recording in my home office once again. Thank you to everyone that watched the last video. I had some really very kind comments, and a change of scenery certainly seemed to go down very well. Or possibly it was that segment at the end, just after I'd recovered from a fall, that people enjoyed. Schadenfreude at seeing me in pain, perhaps. Well, now that I'm back, AI is absolutely everywhere at the moment. With the latest release of generative AI models, AI has hit mainstream public consciousness like never before. It's not even a question of seeing one or two stories about AI in the mainstream news anymore. Every day seems to bring multiple different stories about something remarkable that has been done with ChatGPT or DALL-E 2 or Stable Diffusion, or any one of the many other generative AI systems that are out there. Some of these stories are about the ways in which these systems produce errors, or can be tricked into producing errors relatively easily. We've all seen examples of almost photorealistic humans generated by text-to-image systems, where it takes a moment to spot that the people have 6 fingers or an extra arm. Similarly, my social media feeds have been full of examples of ChatGPT being convinced that 100 plus 100 is 250, or some other basic mathematical error. These easy to spot examples of errors are hardly the real problem with generative AI. It's the errors that go unnoticed that are the real problem. Issues with bias can be very subtle indeed. As these systems become more and more embedded in everyday life, the areas where those biases might manifest and become problematic increase exponentially. It's worth thinking about how these generative AI systems work and how we might discover and measure those biases. Most of the current cutting-edge systems rely on transformer models with self-attention layers, following the work described in Google's seminal paper from 2017, Attention is All You Need. Transformer models have since been used in OpenAI's GPT family of large language models and competing NLP systems from other groups. They've been used in image generation technologies, including Google's Imagen, OpenAI's DALL-E 2, and even used in generalist AI models like DeepMind's Gato. Transformers rely on tokenized input to function. If we take a typical text input model and think of something like GPT or an image model like Imagen, there'll be a word encoding layer within the system. In the diagram, we can see that the architecture of a natural language processing system similar to that used in the GPT models. Our text prompt is first broken into tokens. If the text is shorter than the expected number of tokens, in this case 2048, padding will be added. If our text is longer than the token limit, only the final 2048 tokens of the input will be used. And now let's take a look inside the AI model. The first task for AI is to make sense of the input in a way that the computer understands. And how do we get the computer to understand that red, blue, yellow and green should be associated with each other as colours, or that dog, cat, rabbit and goldfish might all be connected as common types of pet? Since the computer sees words as a string of numerical values associated with their letters, some other encoding layer that places words in context with each other is needed, and this is the purpose of a word encoding layer. The tokens representing each word or part word are fed into that layer, and it then converts each into a column vector of similar size. In the example on screen, the vector is 1600 numbers long, and you can think of that vector as plotting the location on a graph. But instead of just the usual two x and y axes, this graph has a whopping 1600 axes, all at right angles to each other, in some impossible to visualize higher dimensional space. It slightly breaks my brain to try and imagine it, so let's reduce back to 3 dimensions for present purposes. Here we see a sort of word space, with words with similar meanings grouped near each other. Pets are gathered together within possibly a cloud of other animals. Colours are located in a different part of the word space, verbs in yet another part, and so on. You can imagine that the whole dictionary is represented floating within this lexical galaxy. That's all well and good, and it makes for some pretty pictures, but what's the consequence of that? Well, thanks to these coordinates in higher dimensional word space, the computer understands the conceptual relationships between words. As we saw in the last video, the training gradually optimizes the weights of all of the links between neurons. Training a word encoding layer means optimizing the links between the 50,000 or so words or part words in our dictionary and the 1,600 neurons encoding the meaning of the words. Once trained, lots of subtlety will be encoded. White, black, red, blue and green might all be colours, but the locations of green will also track with concepts like environment, red with concepts like danger, and blue with concepts like depression or sadness, as well as the simple colour meanings. Once every word is represented by a 1,600 long vector made up of numbers, that list of coordinates in our word space effectively, we can now carry out mathematical operations to examine the relationships between words. What are the nearest other words to cat? In a fully trained model, we see words like kitten, tabby, feline and moggy nearby to cat. If we subtract the values of the word woman from the word queen and then add in the value for the word man, we land in a place near to the word for king, showing that that male-female relationship is shared across these various different terms. For other words, this is where evidence of bias can start to be present. If white, black, brown or yellow potentially encodes for ethnicity as well as simple colour, then it becomes interesting to measure how close those words are to others representing positive or negative characteristics. If it turns out that negative characteristics are located nearer to one colour or positive ones located to another colour, then you can literally measure the bias in the system. The same approach can reveal biases around gender, sexuality, ability, age, and other characteristics. A system that has closely correlated positive or negative characteristics with particular aspects of identity will inevitably then make decisions reflecting those biases. It's one thing for an image generation AI meant as a technical curiosity to have a tendency to create images of white males in response to the word lawyer. It's an entirely more serious matter if a similarly biased word encoding system is then sifting CVs and determining access to the profession. There are some rough and ready sticking plaster fixes that can be applied. Training, after all, is expensive. You can't go back and retrain your entire AI to avoid bias if you discover it afterwards. You can add a thin filter layer between the user and the AI, and this filter might spot examples of nouns in input text and then randomly and invisibly to the user add characteristics to them before they're fed into the AI, so that now any instance of perhaps the word lawyer might become young female South Asian lawyer or elderly male black lawyer, and this invisible prompt engineering then combats the inherent bias that might otherwise be present in the trained model itself. So whose fault is it that these AI systems might be biased in the first place? The insidious thing about all of this is that no one is necessarily choosing to make systems biased in this way. It's something that the systems learn for themselves, reflecting the inherent biases in the corpus of data used to train them. Because these very large language models require huge amounts of data to train them, often a substantial portion of the training dataset has been derived from online sources such as the Common Crawl. Other content might come from public domain texts, such as out of copyright books. Even where these sources are good quality in terms of their text content, they still reflect the social mores of their time. Online sources will contain both the best and worst of internet text content. For anyone looking to use these systems or build other AI solutions on top of them, understanding exactly where the biases are, how they arise, how to find and measure them, and then how to apply fixes to a greater or lesser extent will be critical. This is important both for public trust and confidence as these systems become ever more prevalent, and to avoid legal complications with everything from anti-discrimination laws to existing rules around automatic decision making. AI is here to stay, and it is imperative that people understand and trust these systems, understanding bias and combating that is a key part to building public trust.